Hello, in this lecture we'll answer on two questions. In the first question we'll find out the value of line segment DE that is equal to x, and in the second question we will find out the value of the shaded area that is inside this quarter circle. So we start with the first question. In the drawing we have triangle ABC. We know that angle ABC equals to 30 degrees. Angle ACB also equals to 30 degrees. Angle DAE equals to 60 degrees. And also line segment BD equals to 5 units. And line segment EC equals to 4 units. And our mission is to find out the length of line segment DE that is equal to x. So first of all, we'll focus on triangle ABC. You know that in triangle ABC, angle ABC this angle is equal to angle ACB, and both angles they are equal to 30 degrees. I'll repeat again. In triangle ABC, angle ABC equals to angle ACB, and both angles they are equal to 30 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in a triangle there are equal sides. So in front of this angle we have side AB, in front of this angle we have side AC, and according to the rule that I mentioned, AB must be equal to AC. Okay, side AB must be equal to side AC. Okay, so those two sides they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees, so we'll define angle BAD as alpha, and we'll define angle EAC, this angle, as beta, and we know that the sum of the angles in triangle ABC must be equal to 180 degrees. So which angles we have in triangle ABC? This angle equals to 30 degrees, plus this angle that is also equals to 30 degrees, plus this angle that is equal to alpha, plus this angle that is equal to 60 degrees, plus this angle that is equal to beta according to our definition. In total, the sum of those all angles, they must be equal in total to 180 degrees. So here this equation states that the sum of the angles in triangle ABC equals to 180 degrees. So here we have 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees, plus alpha plus beta. In total they must be equal to 180 degrees. So here we subtract 120 degrees from this equation, and we get that alpha plus beta equals to 180 degrees minus 120 degrees, it is equal to 60 degrees. So in conclusion, we found out that alpha plus beta equals to 60 degrees. In the next step, we'll do two constructions. So the first construction is that from point A, we'll draw a straight line in such a way that the angle between the straight line and side AC will be equal to alpha. So here, this angle equals to alpha according to our construction, and we'll do also a second construction from point C, this point. We'll draw a straight line in such a way that the angle between the straight line and side AC will be equal to 30 degrees. Here again, this angle equals to 30 degrees according to our construction. In the next step, we will extend the two straight lines until they intersect with each other, and we will define the intersection point between the two straight lines here as point F. So we created here triangle AFC, and in the next step we will prove that triangle AFC is congruent to this triangle ABD. Okay, so I write it down. We will prove the triangle ABD, this triangle is congruent to this triangle, that is triangle AFC, the new triangle that we constructed. Okay, so why triangle ABD is congruent to triangle AFC? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. So here angle BAD, this angle, is equal to this angle that is actually angle CAF. They are both equal to alpha, therefore they are equal to each other. I'll repeat again. Angle BAD in triangle ABD is equal to angle CAF in triangle AFC, and they're both equal to alpha, therefore they are equal to each other. In addition, those two sides, that is to say side AB is equal to side AC according to what we have already proved, that side AB equals to side AC. So here we write down that side AB equals to side AC according to what we have already proved. And finally, those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So here, this angle, that is actually angle ABD, is equal to this angle, that is angle ECA, and both angles, they are equal to 30 degrees, therefore they are equal to each other. I'll repeat again. Angle ABD equals to angle ECA, both angles are equal to 30 degrees, therefore they are equal to each other. So we actually proved that this triangle ABD is congruent to this triangle AFC according to according to angle side angle similarity rule. According to angle side angle rule. According to angle side angle rule. I'll repeat again. We actually proved that triangle ABD is congruent to triangle AFC according to angle side angle rule. Okay, so I will explain what I mean. Those two triangles congruent to each other according to angle side angle rule. That is to say, those two angles that are alpha and 30 degrees and the side that is attached to those two angles, that is actually side AB in triangle ABD, are correspondingly congruent to those two angles that are actually alpha and 30 degrees, and the side that attached to those two angles that is actually side AC in triangle AFC. Therefore, those two triangles congruent to each other according to angle side angle rule. And for the fact that those two triangles congruent to each other, we'll conclude two things. The first thing that we will conclude that side BD equals to side FC. Side BD equals to side FC according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the corresponding sides, that is to say BD and FC, will be equal to each other. But according to what is given us in the question, side BD equals to 5 units. So we can write down that BD equals to 5 units. And for this equation 5 equals to BD equals to FC, we will derive that side FC is also equals to 5 units. Okay? Here side FC equals to 5 units. And the second thing that we will conclude from the fact that those two triangles can go into each other is that side AD equals to side AF. AD equals to AF according to the same rule that corresponding sides and congruent triangles are equal to each other. And if we define side AD as A, here side AD equals to A according to our definition, then from this equation A equals to AD equals to AF, we'll derive that side AF is also equals to A. Okay, here side AF equals to A. In the next step, we will join points E and F together by a straight line. And we will prove that the green triangle, triangle ADE, is congruent to the orange triangle, triangle AEF. Okay, we prove that the green triangle congruent to the orange triangle. But before that, we have already proved that alpha plus beta equals to 60 degrees. So this angle, angle FAE, that is equal to alpha plus beta, it is equal to 60 degrees, according to what we have already proved. So, we will prove that the green triangle, triangle ADE, is congruent to the orange triangle, triangle AEF. So, why those two triangles can go into each other? First of all, we just right now proved that side AD equals to side AF, and side AD equals to side AF, and they're both equal to A. according to our definition. In addition, those two angles, they are both equal to 60 degrees, therefore they are equal to each other. So this angle, it is actually angle DAE in the green triangle, is equal to this angle, that is angle EAF in the orange triangle. And they are both equal to 60 degrees, therefore they are equal to each other. I'll repeat again. Angle DAE in the green triangle equals to angle EAF in the orange triangle. They are both equal to 60 degrees, therefore they are equal to each other. And finally, this side, side AE, is a common side that belongs to both triangles. So side AE equals to itself. AE equals to AE. It's a common side that belongs to both triangles. Okay. Here. AE equals to AE is a common side that belongs to both triangles. So we actually proved that the green triangle, triangle ADE, is congruent. This is the sign of congruent to the orange triangle, triangle AEF. According to side angle side rule. Those two triangles congruent to each other according to side angle side rule. I'll explain what I mean. Actually, those two sides and the angle that is included between those two sides in the green triangle congruent to those two sides and the angle that is included between those two sides in the orange triangle. Therefore, the green triangle is congruent to the orange triangle according to side angle side rule. And for the fact that those two triangles congruent to each other, we conclude that side DE equals to side EF. Okay, we conclude that side DE equals to side EF. Side DE in the green triangle equals to side EF in the orange triangle. DE equals to EF. But according to what is given us in the question, DE equals to X. So we can write down that DE equals to X. And from this equation, X equals to DE equals to EF, we will derive that EF is also equals to X. EF is also equals to X, so EF equals to X. Okay. So, in the next step, I will present the law of cosines, and we will implement the law of cosines in this triangle, triangle EFC. So, what is the law of cosines? The law of cosines is true in any triangle. I've already mentioned this before, a couple of times. So, in any triangle, so if we have a triangle ABC that could be any triangle, this is triangle ABC. And we know that side AB equals to A units in its length, side AC equals to B units in its length, and the angle between side AB and side AC is theta, and side BC equals to C units in its length. Then, according to the law of cosines, the following equation is true, that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. I'll repeat again. In this triangle ABC, that could be any triangle, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Okay, so we implement the law of cosines in this triangle EFC. So I'll copy this triangle here in this page, and we'll implement the law of cosines in this triangle EFC. Okay. Angle ECF, this angle equals to 30 degrees plus 30 degrees, that is 60 degrees. This angle equals to 60 degrees. So this is triangle EFC that I copied from the original drawing. So according to the law of cosines, we will get that in triangle EFC, x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. I'll repeat again. We implemented the law of cosines in this triangle EFC, and according to the law of cosines, x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. So here, x squared equals to 4 squared, that is 16, plus 5 squared, that is 25, minus 2 times 4 is minus 8, and minus 8 times 5 is minus 40. So it is minus 40 times cosine 60 degrees, and cosine 60 degrees equals to 1/2. So in total, this expression equals to minus 40 times 1/2. So we actually found out that x squared equals to 16 plus 25 is 41, and minus 40 over 2 is minus 20. So x squared equals to 41 minus 20, that is 21. So x squared equals to 21. Here we take out of this equation, and we get that x equals to either to the positive square root of 21, or in terms of numbers, it is equal to 4.58 units. And the reason that we took only the positive square root of 21 is because of the fact that x is a length, and as a length it must be a positive number. So the answer to the question is that line segment DE that is equal to x, it is equal to either the positive square root of 21, or in terms of numbers it is equal to 4.58 units. Okay, so we finished with the first question. The next step, I will present to you the second question. in the drawing we have a quarter circle. Inside this quarter circle we have a circle and a semicircle that are tangent to each other at this point, and we also have here this circle that is tangent to the quarter circle at this point. And our mission, and we also know that the radii of both the circle and the semicircle is equal to 2 units. And our mission is to find out the value of the shaded area. So because of the fact that this is a quarter circle, it means that this point is the center of the quarter circle. So here we define this point as point O, and point O is the center of the quarter circle. And here this angle equals to 90 degrees. So this angle equals to 90 degrees. And this is true in any quarter circle. And we also know that if we define this point as point A and this point as point B, then OA and OB are the radii of the quarter circle. So I write it down. So here I will write it here that OB is the radius of the quarter circle. This is the radius of the quarter circle, and OA, it is also the radius of the quarter circle. Okay, radius of the quarter circle. QC is abbreviation for quarter circle. Okay, and here we have OA is the radius of the quarter circle, but it is also tangent to this circle at this point. So we'll define this point as point M. Point M is the point of tendency of tangent OA with this circle. And we have here rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here we have tangent AB that is tangent to this circle at point M. Point M is the point of tendency of tangent AB with this circle. And whenever you have here we have the radius OM that is drawn to the point of tendency. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, then it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. Actually, we can implement rule number 1 in our drawing, because in our drawing, here we define the center of this circle as point P. Point P is the center of the circle. Point M is the point of the circle itself. That is to say, PM is the radius of this circle that is equal to 2 units according to what is given as the question. So here we have the radius PM that is drawn to the point of tendency. That is to say, the radius PM is drawn to point M, that is the point of tendency of tangent AO with this circle. And whenever you have a radius that is drawn to the point of tendency, then according To rule number 1, tangent OA will be perpendicular to the radius MP. So if OA is perpendicular to MP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. In the next step, from the center of this angle, that is to say from point P, we will draw perpendicular on BO. Okay. So here, this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. And we will define the touching point of the perpendicular from point P and BO as L. L is the touching point of the perpendicular from point P and BO. Okay? So actually, we created here quadrilateral LPOM, and inside quadrilateral LPOM we have 1, 2, 3 right angles. Again, inside quadrilateral LPOM we have 1, 2, 3 right angles. So I write it down. I repeat again that inside this quadrilateral we have 3 right angles, and the sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of this angle, the fourth angle, that is actually angle LPM. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay? 270 degrees plus the size of the fourth angle must be equal to 360 degrees. Here we subtract 270 degrees from this equation, and we get that the missing angle LPM, equals to 360 degrees minus 270 degrees, it is equal to 90 degrees, that is to say it is a right angle. So here, angle LPM, this angle, it is a right angle. So we actually found out that inside quadrilateral LPOM we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral LPOM as a rectangle. Quadrilateral LPOM is a rectangle. Okay. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, the opposite sides of rectangle LPOM must be equal to each other. So it means that side PM must be equal to side LO. PM equals to LO. I'll repeat again. Side PM equals to side LO, according to the rule that the opposite sides of a rectangle are equal to each other. But we know that PM equals to 2 units. So we can write here that PM equals to 2 units. And from this equation, 2 equals to PM equals to LO. We derive that LO is also equals to 2 units. LO is also equals to 2 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that side LP must be equal to side OM. Okay, so LP equals to OM, according to the same rule. Okay. Side LP equals to side OM. So if we define side LP as X, here side NP equals to x according to our definition. Then from this equation x equals to LP equals to OM, we derive that side OM is also equals to x. Side OM equals to x. Okay, this side OM equals to x. In the next step, we will focus at this point, that is actually the point of tendency between the circle and the quarter circle. We'll define the point of tendency of the touching point between the circle and the quarter circle as point K. So actually, the quarter circle and the circle have an internal notch between them at point K. That is to say, they are touching each other internally at point K. And whenever you have two circular shapes that are touching each other internally, whenever you have two circular shapes that have an internal notch between them, that is to say they are touching each other internally, or they have an internal notch between them, then the straight line that joins their centers together must pass through their touching points. I repeat again, whenever you have two circular shapes that have an internal notch between them, then the straight line that joins their centers together must pass through their touching point. So here point O is the center of the quarter circle, point P is the center of the circle, and the straight line that joins their centers together is the straight line OP. So this straight line OP, according to the rule that I mentioned, must pass through point K, that is their touching point. Okay? Or in other words, line segment OPK is one straight line. So write it down. Line segment OPK is one straight line. Or in other words, we can also say that points O, P, and K, they are all located on the same straight line. Okay? So, if OPK is a straight line, then OK itself must be also a straight line. So here we can write down that OK is also a straight line. OK is a straight line. What is the definition of line segment OK? Point O is the center of the quarter circle. Here, point O is the center of the quarter circle. Point K is a point on the quarter circle itself. This is exactly the definition of a radius. That is to say, line segment OK is the radius of the quarter circle. Okay, so we can write down that line segment OK is the radius of the quarter circle. Okay, so we'll define the radius of the quarter circle as capital R. Therefore, we can write down that OK, line segment OK, equals to capital R, according to our definition. So here, OB, it is also the radius of the quarter circle. That is to say, it is also equals to capital R. And OA, it is also the radius of the quarter circle, that is equal to capital R also. Okay? And OK, it is also the radius of the quarter circle, that is equal to capital R. So here, Point P is the center of the circle. Point K is the point of the circle itself. Therefore, PK is the radius of this circle that is equal to 2 units according to what is given us the question. So I can write down that PK is the radius of the circle that is equal to 2 units. So in conclusion, we found out that PK equals to 2 units and OK equals to capital R, that is the radius of the quarter circle. And what is the length of line segment PO or OP? The length of line segment OP, it is very easy to see from the drawing that the length of line segment OP equals to OK minus PK. Again, OK minus PK equals to OP. So OP equals to OK minus PK. OP equals to OK. OK is the radius of the quarter circle that is equal to capital R minus PK. PK is the radius of the circle that is equal to 2 units. So in conclusion, we found out that line segment OP equals to capital R minus 2. Line segment OP equals to capital R minus 2. Yeah. Line segment OP equals to capital R minus 2. So in the next step, I will copy the right triangle OPM in a new page, and we will implement the Pythagoras theorem on this triangle OPM. Okay? We just right now found out that the hypotenuse OP equals to capital R minus 2. Side PM equals to 2 units, it is the radius of the circle, and OM equals to X. So this is the right triangle OPM that I copied from the original drawing. So we will implement the Pythagoras theorem on this right triangle OPM. So here, by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, in the right triangle OPM, the square of the hypotenuse is OP squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to OM squared plus PM squared. So here, OP equals to capital R minus 2, therefore OP squared equals to capital R minus 2 squared. And it is equal to OM squared. OM equals to X, so OM squared equals to X squared plus PM squared. PM equals to 2, therefore PM squared equals to 2 squared, that is 4. So in conclusion, we found out that according to equation number 1 and according to the Pythagoras theorem, R minus 2 squared equals to X squared plus 4. Here we will open the brackets on this side of equation number 1, and we get that R minus 2 squared equals to R squared plus 2 squared, that is 4, minus 2 times R times 2 is minus 4R, and it is equal to X squared plus 4. So here we have 4 on both sides of equation number 1, so 4 will get cancelled. What is left on equation number 1 after we cancelled 4? In this side of the equation we have x squared that is equal to r squared minus 4r. So according to equation number 1, we found out that x squared equals to r squared minus 4r. In the next step, we will focus at this point, that is actually the point of tendency of the semicircle and the circle, or the touching point of the semicircle and this circle. So we will define this touching point as point T. So what is actually point T? Point T is the touching point of the circle with the semicircle. Actually, at point T, the circle and the semicircle have an external notch between them. I'll repeat again. The circle and the semicircle have an external notch between them at point T. That is to say, they are touching each other externally at point T. Okay, so we'll define the center of the semicircle as point Q. And I'll repeat again that at point T, the circle and the semicircle have an external notch between them. And whenever you have two circular shapes that have an external notch between them, then the straight line that joins their centers together must pass through the touching point, through their touching point. I repeat again, whenever you have two circular shapes that have an external notch between them, then the straight line that joins their centers together must pass through their touching point. So here, point P is the center of the circle, point Q is the center of the semicircle, and the straight line that joins their centers together is QP. And according to the rule that I mentioned, the straight line QP must pass through point T. Okay, I'll repeat again, according to the rule that I mentioned, the straight line QP that joins their centers together must pass through their touching point, that is point T. Or actually, in other words, QTP is one straight line. I'll write it down. QTP, line segment QTP is one straight line. Or we can also say it differently, that points Q, T, and P, they are all located on the same straight line. This is exactly like saying that QTP is one straight line. Okay? So what is the length of the straight line QT? First of all, so we found out that QTP is a straight line. So if QTP is a straight line, it means that QP is also a straight line. Okay? QP is a straight line. QP is a straight line. So what is the length of the straight line QP? What is the length of the straight line QP? It is very easy to see from the drawing that the length of the straight line QP equals to QT plus TP. QT plus TP equals to the length of the straight line QP. And repeat again, the length of the straight line QP equals to QT plus TP. Okay, so QP equals to, here, point Q is the center of the semicircle. Point T is the point on the semicircle itself. So this is exactly the definition of a radius. That is to say, QT is the radius of this semicircle that is equal to 2 units. Likewise, point P is the center of the circle. Point T is the point on the circle itself. So PT is the radius of the semicircle that is also equal to 2 units. So in conclusion, we found out that Q2 equals to 2 units and TP also equals to 2 units. So here we know that QP equals to QT plus TP. That is to say QP equals to QT that is equals to 2 units plus TP that is also equals to 2 units. So in conclusion, we found out that QP equals to 2 plus 2 that is 4. So in conclusion, we found out that the length of the straight line QP is 4 units. QP equals to 4 units. In the next step, we find out the length of line segment QB. What is the length of line segment QB? Point Q is the center of the semicircle. Point B is the point on the semicircle itself. This is exactly the definition of a radius. That is to say, QB equals to the radius of this semicircle that is equal to 2 units according to what is given as the question. And what is the length of line segment QL? Actually, it is very easy to see it from the drawing that the length of line segment QL equals to BO, that is the radius of the semicircle, minus BQ minus LO. Again, the length of line segment QL equals to BO minus BQ minus LO. I'll write it down. QL equals to BO, that is the radius of the quarter circle, minus BQ, that is the radius of the semicircle, minus LO, that is equal to 2 units. Okay, so I write it down here. So I wrote it down here and we found out actually that QL equals to BQ, QL equals to BO, that is the radius of the quarter circle, minus BQ, that is the radius of the semicircle, minus LO, that is equal to 2 units. So here QL equals to BO, that is the radius of the quarter circle, that is equal to capital R, according to our definition, minus BQ, that is equal to 2 units, this is the radius of the semicircle, minus LO, that is equal to 2 units. So in conclusion, found out that QL equals to capital R minus 2 minus 2, minus 2 minus 2 is minus 3, minus 2 minus 2 is minus 4, so QL equals to capital R minus 4. So in conclusion, we found out that QL equals to capital R minus 4. Okay, QL equals to capital R minus 4, so we can write down here that QL equals to capital R minus 4. In the next step, I will copy the right triangle QLP in a new page, and we will implement the Pythagoras theorem in the right triangle QLP. Okay. LP equals to X. We just right now found out that QL equals to capital R minus 4. And the hypotenuse QP, we've already found out that the hypotenuse QP equals to 4 units. So this is the right triangle QLP that I copied from the original drawing. So we will implement the Pythagoras theorem on this right triangle QLP. So here I write down by PT, that is abbreviation for Pythagoras theorem. So according to the Pythagoras theorem in the right triangle QLP, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here the square of the hypotenuse is QP squared, and it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to QL squared plus LP squared. I repeat again, according to the Pythagoras theorem, in the right triangle QLP, QP squared equals to QL squared plus LP squared. QP equals to 4, this is the hypotenuse, therefore QP squared will be equal to 4 squared, that is 16, and it is equal to QL squared. QL equals to x, therefore QL squared equals to x squared, plus, actually, LP equals to x, therefore LP squared equals to x squared, and QL equals to capital R minus 4, therefore QL squared equals to capital R minus 4 squared. So in conclusion, we found out that according to the Pythagoras theorem and according to equation number 2, 16 equals to x squared plus R minus 4. 16 equals to x squared plus R minus 4 squared. Here we will open the brackets on this side of equation number 2, and we will get that according to equation number 2, 16 equals to x squared plus R minus 4 squared equals to R squared plus 4 squared, that is 16, minus 2 times R times 4 is minus 8R. So here we have 16 on both sides of equation number 2, so 16 will get cancelled. And what is left from equation number 2 after we cancel 16? In this side, nothing is left, so we have 0. That is equal to x squared plus R squared minus 8R. So here we will add 8R to this equation number 2, and we get that according to equation number 2, zero plus 8R is 8R, and it is equal to x squared plus R squared. So according to equation number 2, we found out that 8R equals to x squared plus R squared. Here we will subtract R squared from this equation number 2, and we get that according to equation number 2, 8R minus R squared equals to x squared. Okay, so according to equation number 2, we found out that x squared equals to 8R minus R squared, while according to equation number 1, we have already found out that x squared equals to x squared equals to R squared minus 4R. So we have two different expressions for x squared. Therefore, we create equation number 3 that states that x squared according to equation number 1 must be equal to x squared according to equation number 2. So here x squared according to equation number 1 is equal to r squared minus 4r, and it must be equal to x squared according to equation number 2 that is equal to 8r minus r squared. Okay? So according to equation number 3, r squared minus 4r equals to 8r minus r squared. So here we will add r squared to this equation, equation number 3, and we will get that according to equation number 3, r squared plus r squared is 2r squared minus 4r, that is equal to 8r. So here we will add 4r to this equation, equation number 3, and we will get that according to equation number 3, 2r squared minus 4r plus 4r is 0, and it is equal to 8r plus 4r is 12r. So in conclusion, we found out that according to equation number 3, 2r squared equals to 12r. Here we will divide this equation, equation number 3 by 2, and we will get that according to equation number 3, 2r squared over 2 is r squared, and it is equal to 2r, 12r over 2 is 6r. So in conclusion, according to equation number 3, we found out that r squared equals to 6r. Here we subtract 6r from this equation, equation number 3, and we get that according to equation number 3, r squared minus 6r equals to 0. So here we take r as a current factor from this equation, equation number 3, and we get that according to equation number 3. So we took r as a current factor from this equation. So what is left from r squared after we took from it r as a current factor? What is left is actually r. And what is left from minus 6r after we took from it r as a current factor? What is left is actually minus 6. So in conclusion, we found out that according to equation number 3, r times r minus 6 equals to 0. So here we will have two solutions that are possible for r. The first solution is that r equals to 0. But because of the fact that r is the radius of the quarter circle, r is a length, and as a length it must be a positive number. It can never be equal to 0, so we cancel this solution, and therefore we left only with the second solution, that r minus 6 equals to 0. Here we will add 6 to this equation, and we get that r equals to 6. So we found out that the radius of the semicircle equals to 6 units. Therefore it is very easy to find out now the area of the quarter circle. It will be equal to the area of the circle, that is pi r squared over 4, and r equals to 6 units. And what is the value of the shaded area? The value of the shaded area will be equal, it is very easy to see from the drawing, that the value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. I'm repeating again. The value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. Okay, so the value of the shaded area equals to the area of the quarter circle that I've already mentioned, that the area of the quarter circle equals to pi r squared over 4 and r equals to 6 units according to what we have already found out, minus the area of the circle that is pi r squared and r equals to 2, so it is pi 2 squared, minus the area of the semicircle, that is the area of the circle that is the area of the circle over 2. The area of the circle is pi r squared, the area of the semicircle will be equal to pi r squared over 2 and r equals to 2, so it is pi 2 squared over 2. So in conclusion, we found out that the value of the shaded area equals to the area of the quarter circle that is equal to pi r squared over 4, minus the area of the circle that is pi 2 squared, minus the area of the semicircle that is pi 2 squared over 2. Okay, so here we already found out that the radius of the quarter circle equals to 6, so r equals to 6, therefore r squared is 6 squared, that is 36. So in total, this expression equals to 36 pi over 4. That is the area of the quarter circle minus pi 2 squared. 2 squared is 4 and 4 times pi is 4 pi. That is the area of the circle minus the area of the semicircle, that is pi 2 squared over 2. 2 squared is 4 and 4 over 2 is 2. 2 times pi is 2 pi. 2 pi is the area of the semicircle. So here we found out actually that 36 over 4 is 9, 9 times pi is 9 pi. So in total this expression equals to 9 pi, minus the area of the circle that is 4 pi, minus the area of the semicircle that is 2 pi. So here we actually found out that the value of the shaded area equals to 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. Okay, so I write it down. We found out that the value of the shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Okay, repeat again. The value of this shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. So we finished with the second question. In the next step, I will summarize the lecture. We'll start with the first question. So in the drawing we have triangle ABC, angle ABC equals to 30 degrees, angle ACB also equals to 30 degrees, angle DAE equals to 60 degrees, line segment BD equals to 5 units, line segment CE equals to 4 units, and our mission is to find out the length of line segment DE that is equal to X. Okay, so we focus on triangle ABC. In triangle ABC, we have those two angles that are equal to each other, they are both equal to 30 degrees. So inside triangle ABC, we have angle ABC that is equal to angle ACB, and they are both equal to 30 degrees, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle, there are equal, in front of equal angles in the triangle, there are equal sides. So in front of this angle we have side AB, in front of this angle we have side AC, and according to the rule that I mentioned, those two sides must be equal to each other because they are located in front of those two equal angles. That is to say, side AB equals to side AC. And we also know that the sum of the angles in any triangle is 180 degrees, and especially in triangle ABC. So we define this angle BAD as alpha. We define this angle EAC as beta. And we know that the sum of the angles in triangle ABC is equal to 180 degrees. So which angles we have in triangle ABC? We have this angle that is equal to 30 degrees, plus this angle that is equal to 30 degrees. Also, this angle equals to alpha, this angle equals to 60 degrees, and this angle equals to beta. In total, the sum of all angles here must be equal to 180 degrees. Okay? So here 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees. So in this side of the equation we have 120 degrees plus alpha plus beta equals to 180 degrees. Here we subtracted 120 degrees from this equation and found out that alpha plus beta equals to 180 degrees minus 120 degrees, it is 60 degrees. So alpha plus beta equals to 60 degrees. Then we did a construction. We did actually two constructions. In the first construction, from point A, we drew a straight line in such a way that the angle between the straight line and side AC will be equal to alpha, so this angle equals to alpha according to our construction. Then we did a second construction. From point C, we drew a straight line in such a way that the angle that will be created by the straight line and side AC will be equal to 30 degrees. Again, this angle equals to 30 degrees according to our construction. Then we extended the two straight lines until they intersect with each other at point F. Point F is the intersection point of the two straight lines. Actually, in this way we created triangle AFC, and we proved that triangle AFC is congruent to this triangle ABD. Repeat again, we actually proved that triangle ABD is congruent to triangle AFC. So, why those two triangles congruent to each other? First of all, those two angles are equal to each other. Those two angles are both equal to alpha, therefore they are equal to each other. So here, angle BAD equals to angle CAF, they are both equal to alpha, therefore they are equal to each other. In addition, we have already proved that side AB equals to side AC. Side AB equals to side AC. Here we proved that side AB equals to side AC. And finally, those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So here, angle ABD equals to angle ECA, and they are both equal to 30 degrees, therefore they are equal to each other. So actually we proved that this triangle ABD is congruent to this triangle AFC according to angle side angle rule. So what is angle side angle rule? We actually proved that those two angles that are alpha and 30 degrees and the side that attached to those two angles, that is side AB in triangle ABD, are corresponding congruent to those two angles that are alpha and 30 degrees, and the side that attached to those two angles, that is side AC in triangle AFC. Therefore, we proved that those two triangles congruent to each other according to angle side angle rule. As for the fact that those two triangles congruent to each other, we conclude that side BD equals to side FC. Here, side BD equals to side FC according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding sides, that is to say side BD and side FC, must be also equal to each other. But according to what is given as the question, side BD equals to 5 units. So we can write here that BD equals to 5 And from this equation, phi equals to BD equals to FC, we will derive that FC is also equals to 5 units. Here, side FC also equals to 5 units. And the second thing that we conclude from the fact that those two triangles can go into each other is that side AD equals to side AF. Side AD equals to side AF according to the same rule that corresponding sides corresponding sides that can go in triangles are equal to each other. Okay, those two triangles can go into each other, therefore the two corresponding sides, that is to say AD and AF, must be also equal to each other. And if we define AD as A, here AD equals to A according to our definition, then from this equation A equals to AD equals to AF, we will derive that AF is also equals to A. Here, AF equals to A. In the next step, we joined points E and F together by a straight line, and we proved that the green triangle is congruent to the orange triangle. The green triangle ADE is congruent to the orange triangle AEF. So, why those two triangles can go into each other? First of all, we just right now proved that side AD equals to side AE equals to A. Side AD equals to side AF, and they are both equal to A. Therefore, they are equal to each other. In addition, we know that alpha plus beta equals to 60 degrees here. We already proved that alpha plus beta equals to 60 degrees. So those two angles, they are both equal to 60 degrees, therefore they are equal to each other. So here we can, those two angle DAE in the green triangle equals to angle EAF in the orange triangle, and they are both equal to 60 degrees, therefore they are equal to each other. And finally, side AE is a common side that belongs to both triangles, so side AE equals to itself. It's a common side. AE equals to AE is a common side that belongs to both triangles. So we actually proved that the green triangle is congruent to the orange triangle according to side angle side rule. Okay, according to side angle side rule. Well, I will explain what I mean. Here, the green triangle, in the green triangle we have those two sides, and the angle that is located between those two sides are correspondingly congruent to those two sides, and the angle that is included between those two sides in the orange triangle. Therefore, we proved that those two triangles can go into each other according to side angle side rule. We have two sides, and the angle between those two sides in the green triangle that are congruent to two sides, and the angle between those two sides in the orange triangle. Therefore, they are congruent to each other according to side angle side rule. And from the fact that those two triangles can go into each other according to side angle side rule, we conclude that side DE equals to side EF. Here, side DE equals to side EF. According to the same rule that corresponding sides in congruent triangles are equal to each other. But according to what is given as the question, side DE equals to X. So I can write here that D equals to X, and from this equation X equals to D equals to EF, we will derive that EF is also equals to X. Here, side EF also equals to X. Then I presented to you the law of cosines, and we implemented the law of cosines in this triangle, triangle EFC. So what is the law of cosines? The law of cosines is true in any triangle. So if we have this triangle, triangle ABC, that could be any triangle, and we know that side AB equals to A units in its length, side AC equals to B units in its length, and the angle between side AB and side AC is theta, and side BC equals to C units in its length, then according to the law of cosines, the following equation is true, that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Again, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Then we implemented the law of cosines in this triangle, triangle ECF. Side FC equals to 5 units, side EC equals to 4 units. And we just right now found out that side FE equals to X. And here, this angle FCE equals to 30 degrees plus 30 degrees, that is 60 degrees. So we implemented the law of cosines in this triangle EFC according to the law of cosines. X squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. Again, x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. So here x squared equals to 4 squared, that is 16, plus 5 squared, that is 25, minus 2 times 4 is minus 8, and minus 8 times 5 is minus 40, and cosine 60 degrees is 1/2, so we substituted cosine 60 degrees by 1/2. So in total this expression equals to minus 40 times 1/2. So in conclusion, we found out that x squared equals to 16 plus 25 minus 40 over 2. 16 plus 25 is 41, and minus 40 over 2 is minus 20. So in conclusion, we found out that x squared equals to 41 minus 20. 41 minus 20 is 21, so in conclusion, we found out that x squared equals to 21. We took a root out of this equation and we found out that x equals to the positive square root of 21. Or in terms of numbers, it is equal to 4.58 square units. And we took the positive square root of 21 because of the fact that x is a length, and as a length, it must be a positive number. So here, line segment DE that is equal to x, it is equal to either the positive square root of 21, or in terms of numbers, it is equal to 4.58 units. So we finished with the first question, then I presented to you the second question. In the second question, we have in the drawing a quarter circle. Inside this quarter circle, we have a circle and a semicircle that are tangent to each other at point T, and this circle is tangent to the quarter circle at point K. Each radius, the radius of the circle equals to 2 units, and the radius of the semicircle also equals to 2 units. And our mission is to find out the value of the shaded area. So first of all, because of the fact that this is a quarter circle, this point must be the center of the quarter circle, that is to say point O is the center of the quarter circle, and then again QOA is always will be equal to 90 degrees. Okay, and also BO is the radius of the quarter circle, and AO is also the radius of the quarter circle. It is true in any quarter circle. Okay? So, here we have OA, it is not only the radius of the quarter circle, but it is also tangent. It is tangent to this circle is point M. Point M is the point of tendency of tangent AO with this circle. And we have rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. We have tangent AB that is tangent to this circle at point M. Point M is the point of tendency. And we have the radius OM that is drawn to the point of tendency. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if tangent AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. According to this rule number 1. So we can implement rule number 1 in our drawing. Here point P is the center of the circle, point M is the point of the circle itself, therefore PM is the radius of this circle that is equal to 2 units. We have here the radius PM that is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent AO with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular. Tangent AO will be perpendicular to the radius MP. So if AO is perpendicular to MP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. Okay, then from the center of this circle, that is point P, we draw perpendicular on QO. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We defined the touching point of the perpendicular from point P and QO as L, and actually we created here quadrilateral LPOM that has 1, 2, 3 right angles. Okay, inside quadrilateral LPOM we have 3 right angles, and the sum of 3 right angles is 90 times 3, it is 270 degrees, plus the size of the fourth angle, that is actually angle NPM. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So here we subtracted 270 degrees from this equation and found out that the missing angle NPM, equals to 360 degrees minus 270 degrees, it is equal to 90 degrees, so it is a right angle. So this angle is a right angle, so we actually found out that inside quadrilateral LPOM we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral LPOM as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, rectangle LPOM, side PM must be equal to side LO. PM equals to LO, according to the rule that the opposite sides of a rectangle are equal to each other. But PM equals to 2 units, it is the radius of the circle. So we can write here that PM equals to 2, and from this equation 2 equals to PM equals to LP, we will derive that equals to LO. 2 equals to PM equals to LO. We will derive that LO is also equals to 2. Here LO equals to 2. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that LP equals to OM. LP equals to OM. And if we define LP as X, LP equals to X according to our definition, then from this equation X equals to LP equals to OM, we will derive that OM is also equals to X. Here OM equals to X. Then we focus at point K, that is the touching point between the circle and the quarter circle, or the point of tendency between the circle and the quarter circle. Actually, the circle and the quarter circle have an internal notch between them at point K. That is to say, they are touching each other internally at point K. And whenever you have 2 circular shapes that are touching each other internally, then the straight line that joins their centers together must pass through their touching point. Repeat again, whenever you have 2 circular shapes with an internal notch between them, then the straight line that joins their centers together must pass through their touching point. So here, the center of the quarter circle is at point O. The center of the circle is at point P. And the straight line that joins their centers together is the straight line OP. And this straight line must pass for point K, that is their touching point. That is to say, KPO is one straight line. Okay, here, KPO is one straight line. Or we can also say that points O, P, and K, they are all located on the same straight line. Okay? So if OPK is a straight line, then OK must be also a straight line. So OK is a straight line. Okay? And what is the definition of the straight line OK? Point O is the center of the quarter circle. Point K is the point on the quarter circle itself. This is exactly the definition of a radius. That is to say, OK is the radius of this quarter circle, and we define the radius of this quarter circle as capital R. So OK equals to capital R, that is the radius of the quarter circle. And here point P is the center of the circle, point K is the point of the circle itself, So pk is the radius of this circle that is equal to 2 units. So here pk equals to 2, pk equals to 2, and ok equals to capital R. And what is the definition, what is the length of line segment OP? The length of line segment OP will be equal to OK minus PK. Again, OP equals to OK minus PK. I'll repeat again. OP equals to OK minus PK. OK equals to capital R. PK equals to 2. Therefore, OP equals to capital R minus 2. So we found out that OP equals to capital R minus 2. Then I copied the right triangle OPM in a new page, and we implemented the Pythagoras theorem on this right triangle OPM. This is the right triangle OPM that I copied from the original drawing. We just right now found out that the hypotenuse OP equals to capital R minus 2. PM is the radius of the circle that is equal to 2 units, and OM equals to X. This angle equals to 90 degrees according to our construction. This angle equals to 90 degrees according to rule number 1. The tangent to a circle is perpendicular to the radius to its point of tendency. So we implemented the Pythagoras theorem on this right triangle OPM. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The square of the hypotenuse is OP square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to OM square plus PM square. So, in conclusion, according to equation number 1, OP square equals to OM square plus PM square. OP equals to R minus 2, so OP square is R minus 2 square, and it is equal to MO square. MO equals to X, so MO square is X square plus PM square. PM equals to 2, so PM square is 2 square, that is 4. So in conclusion, according to equation number 1 and the Pythagoras theorem, we found out that R minus 2 square equals to X square plus 4. Here we open the brackets on this side of equation number 1, and we found out that R minus 2 square equals to R square plus 2 square, that is 4, minus 2 times R times 2, that is minus 4R. Okay? And the other side of the equation, we have X squared plus 4. So here we have 4 on both sides of equation number 1, so 4 will get cancelled. And what is left from equation number 1 after we cancelled 4? What is left? Actually here, X squared equals to R squared minus 4R. So according to equation number 1, we found out that X squared equals to R squared minus 4R. Then we focused at this point, that is the touching point or the point of tendency of the semicircle and the circle. Okay? Actually, the circle and the semicircle are touching each other at this point. Actually, this is an external line between those two circular shapes. I'll repeat again. We define this touching point as point T. Point T, in point T, those two circular shapes have an external notch between them. Okay? And whenever you have an external notch between two circular shapes, then the straight line that joins their centers together must pass through their touching point. So here, point P is the center of the circle. Point Q is the center of the semicircle. And the straight line that joins their centers together is the straight line QP. And according to the rule that I mentioned, the straight line QP that joins their centers together must pass through point T, that is their touching point. Or in other words, we can say that QTP is one straight line. Okay? Here, QTP is one straight line, and again, we can also say that points Q, T, and P, they are all located on the same straight line. So if QTP is a straight line, then it means that QP is also a straight line. QP is a straight line, and what is the length of the straight line QP? QP equals to QT plus TP. Again, QP equals to QT plus TP. QP equals to QT plus TP. Okay? And here point Q is the center of the semicircle. Point T is the point of the semicircle himself. That is to say, QT is the radius of the semicircle that is equal to 2 units. Likewise, here point P is the center of the circle. Point T is the point of the circle itself. Therefore, TP is the radius of this circle that is also equal to 2 units. So in conclusion, we found out that QT equals to 2 and TP also equals to 2. Therefore, QP that is equal to QT plus TP equals to 2 plus 2. 2 plus 2 is 4, so in conclusion we found out that the straight line QP equals to 4 units. Then we found out the value of line segment BQ. Point Q is the center of the semicircle. Point B is the point of the semicircle itself. So BQ is the radius of the semicircle that is equal to 2 units. And what is the length of line segment QL? The length of line segment QL equals to BO, that is the radius of the quarter circle, minus BQ, that is the radius of the semicircle, minus LO, that is equal to 2 units. I'll repeat again. QL, the length of line segment QL equals to BO, that is the radius of the quarter circle, minus BQ, that is the radius of the semicircle, minus LO, that is equal to 2 units. So here, BQ equals to capital R, that is the radius of the semicircle, BO equals to capital R, that is the radius of the semicircle, BQ equals to 2 units, that is the radius of the semicircle, and LO also equals to 2 units. So in conclusion, we found out that QN equals to capital R minus 2 minus 2. Minus 2 minus 2 is minus 4, so QN equals to capital R minus 4. So in conclusion, we found out that QL equals to capital R minus 4. Then we implemented, I copied the right triangle QLP in a new page, and we implemented the Pythagoras theorem on this right triangle QLP. This is the right triangle QLP that I copied from the original drawing. We just right now found out that QL equals to capital R minus 4. Here this angle equals to 90 degrees according to our construction. LP equals to X. And we have already found out that the hypotenuse QP equals to 4 units. Here, QP equals to 4 units. So then we implemented the Pythagoras theorem on this right triangle QLP. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The square of the hypotenuse is QP square, and it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to QL square plus LP square. So QP equals to, so we found out that QP square equals to QL square plus LP square. Then QP equals to 4, therefore QP square is 4 squared, that is 16, plus LP square. LP equals to X, so LP square is X square, plus QL square. QL equals to capital R minus 4, therefore QL square equals to capital R minus 4 square. Here we open the brackets on this side of equation number 2 and found out that 16 equals to X square plus R minus 4 square. R minus 4 square equals to R square plus 4 square, that is 16, minus 2 times R times 4, that is minus 8R. So we have 16 on both sides of the equation, so 16 will get cancelled. So what is left from equation number 2 after we cancel 16? In this side nothing is left, so we have 0. In the other side we have X square plus R square minus 8R. Here we added 8R to this equation number 2, and we found out that 0 plus 8R is 8R. In the other side of the equation we have 8R minus 8R is 0, so we left only with X square plus R square. So in conclusion, according to equation number 2, 8R equals to X square plus R square. Here we subtracted R square from this equation number 2, and we found out that according to equation number 2, 8R minus R square equals to X square. Okay, so actually we have two different expressions for x squared. According to equation number 2, x squared equals to 8r minus r squared, while according to equation number 1, x squared equals to r squared minus 4r. Then, therefore, we created equation number 3 that states that x squared according to equation number 1 must be equal to x squared according to equation number 2. So x squared according to equation number 1 equals to 2r minus 4, 2r squared minus 4r. X squared according to equation number 1 equals to r squared minus 4r. And it must be equal to x squared according to equation number 2, that is equal to 8r minus r squared. So here we added r squared to this equation, equation number 3, and found out that r squared plus r squared is 2r squared minus 4r, that is equals to 8r. Here we added 4r to this equation, equation number 3, and found out that 2r squared, 4r minus 4r is 0, and it is equal to 8r plus 4r, that is 12r. So in conclusion, we found out that according to equation number 3, 2r squared equals to 12r. So here we divided this equation, equation number 3 by 2, and we got that 2r squared over 2 is r squared, and 12r over 2 is 6r. So in conclusion, we found out that according to equation number 3, r squared equals to 6r. Here we subtracted 6r from this equation, equation number 3, and we found out that r squared minus 6r equals to 0. According to equation number 3, then we took from those two expressions r as a common factor. So what is left from r squared after we took from it r as a common factor? What is left? It is actually r. And what is left for minus 6r after we took from it r as a common factor? What is left? It is actually minus 6. So in conclusion, we found out that according to equation number 3, r times r minus 6 equals to 0. So here we will have two solutions that are possible for r. The first solution for r is that r equals to 0. But because of the fact that r is the radius of this quarter circle, r as a length, it must be a positive number, so it can never be equal to 0. So we cancel this solution, and we left only with the second solution, that r minus 6 equals to 0. Here we added 6 to this equation and found out that r equals to 6 units. So in conclusion, we found out that the radius of this quarter circle equals to 6 units. Therefore, it is very easy to find out the area of the quarter circle. It will be equal to the area of the circle, that is pi r squared, over 4. If we divide it by 4, we'll get the area of the quarter circle. And r equals to 6 units. So what is the area? What is the value of this shaded area? The value of this shaded area, it is very easy to see from the drawing that it will be equal to the area of the quarter circle minus the area of the circle minus the area of the semicircle. I repeat again, the value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. We have already found out that the area of the quarter circle equals to pi r squared over 4 and r equals to 6. The area of the circle equals to pi r squared and r equals to 2, so it is pi 2 squared. And the area of the semicircle equals to to the area of the circle over 2, that is pi r squared over 2, and r equals to 2, so it is pi 2 squared over 2. Okay, then we know that r equals to 6 units, therefore r squared is 6 squared, that is 36. In total, this expression equals to 36 pi over 4 minus pi 2 squared. 2 squared is 4, 4 times pi is 4 pi. So here we have 4 pi, and 2 squared is here pi 2 squared over 2. 2 squared is 4, 4 over 2 is 2, 2 times pi is 2 pi. So this expression equals to 2 pi. And here we have 36 over 4 is 9, so this expression in total equals to 9 pi. So we have 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So in conclusion, we found out that the value of the shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. I'll repeat again, the value of this shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Okay, thank you very much.